Right. All right. Welcome, everybody. So, machine learning is something which changed the analytical world. Okay. And here's a great example. And this is given by McKinsey and Company. Okay. And I'm going to give you some references also here in the next slide. Beautiful references. I would like you to go through those things. So the classical, suppose we have the, this is refers to the heights. This is red means it's a it's a three-dimensional picture. Red means it's going down. This green, bluish green means going up. Okay, the more the more sharper and sharper, it means more sharper the hill is. This is the hill. This is the opposite of hill. Are you with me? Okay. So in terms of observation, that means the importance of this observation. It's a lower level. Let's say it is the surface of the water. Okay, it is something that is spiking out of the water, and this is something that is spiking below the water. Are you with me? It's a three-dimensional picture. This is called isocurves. In mathematics, these are called isocurves. That means they all have the same height. Isocurve, same height in this case. Okay, red means below the surface. Green or bluish green means above the surface. Are you with me now? There are three.
Yes.
In this case, how many hills are there? There is only one hill. Two hills are there. Do you agree with me?
3 hills.
And this is two hills. And this is a hill. Okay. So, if you have, this refers to the intensity of observation, how much observation, how big, so the value of the observation. So, you have to mute on where is that? Okay, please. Okay, thank you. So, so these are, let's say this is a low value, okay? Red means low value, this means high value.
Okay.
When the surface is, at this level, it means normal value. Are you with me?
Yes.
Okay. And this is driver A and this is driver B. Okay. Driver means here, warm. So it says here, warmer colors indicate higher degrees of risk. So you can say it in terms of isocurves, it can be a risk number also. Warmer means high risk, this means low risk. Are you with me? That's another way of thinking. Okay. And, the peaks are more tightly aligned, pinpoint areas of highest risks with more precision than the regression can. Okay, so the point is, this is drivers type or drivers A type drivers, and this is B type drivers. Okay.
Okay.
What we are saying is that, if you're modeling the risk, obviously, a lot of risk is here because a lot more risks are here because this is red. Too many red is there, right? And then it is building, it's kind of bending the curve here towards this one because here, after this, the risks are here. So after it comes up to this, it is bent. This is pulling that, but then afterward, these two are start pulling this, line. And this is a predictive line, and that takes care of these kinds of, very non-linear risks, and regression doesn't take care of this. That's what, McKinsey has put it as an example. I wrote, there are non-parametric methods and non-linear methods are also available. It's my point of view. But anyway, that, they, as well as, they did it to show the importance of machine learning. Because in the machine learning, it will point out only this area alone. It will point out. It will build a model to this one. It will build a model to this one. You know what I'm saying?
Okay.
It's so specific. It will build a model here. It will build a model or regression tree that is giving weight here and then weight here. Okay, things like that. So it is very highly, what should I say, elastic to the needs of the data. And regressions are more restrictive. That is because it's not an apples to apples comparison, but they are saying it. That's okay because they are not the best experts. I'm the best expert. What can I say, right? That's what I have to say. Why do I say that? I'm besides the joke. What I want to say is that there are nonlinear regressions you can build. Okay, there are also there are so many. There are nonlinear regressions. Let me put it this way: there are nonlinear regressions you can build. Okay, but anyway, this is McKinsey, so you can use it to explain what is meant by machine learning because it will give you very specific weights like this here, 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 and here separately, right? This is a positive one, of course. This is a positive one, so I'm going to make it as green color. Okay, this is all. This is also green color because it's a positive one. Okay, but these are red colors, right? Because these are high risks. This is low. These are low risks. Okay, or maybe more profitable.
So you are saying the green circles are more risk?
No, not the greens. That's why I got to change this also color. I want to make it as red because red is always bad, right? So these are all high risks.
The circles means the
It's a
red,
kind of
the red.
it's a kind of the mathematical version of saying that those there is a score here, right? There is a score here on this one.
Okay.
There is a score here. So in fact, when I say driver here, I mean very carefully, listen very carefully. These mean the attributes, drivers, attributes, factors.
Okay.
So for a factor B, a collection of, you should say driver, okay? Factor B, driver B, the score 10 and the score driver A, the factor A, score 80 means high risk. That's what it means.
Okay.
And around that, there's quite a bit of range of values there. Around that is high risk. And again, here, factor B having score 40 and factor A having score 80 or 85 is really low risk. See how nonlinearly it changes, right? And then again, if you come down here, factor 70 on driver or factor. Remember, driver means factor or attribute. Okay. But he also says as a collection of factor. You can call it the PCA, B,
yes.
PCAA. Now you can understand, right?
Yeah.
So the point is, this the factor value is 75 and this is 80. This is a high risk. But such a highly nonlinear, you can see that it's all over, right? Highly nonlinear.
Yes.
And these are huge collection of observations. They score, and that's how they scored. When they scored it, that's how the distributions happen to be. It's not just one person, one point. It's a collection of points here. Okay, that's why it is all there. So in that database, there is a less number of observations here, and also they are all good, right? So the point is, how can we model this? Then they are saying, well, machine learning can do, a very good job of this one because it is actually concentrating on segments of information.
Okay.
That is what the difference between machine learning and regression is. That's how they said it. They are a great consulting company. I want to use that one. That's okay. We can do that. That's all right. And then here is 3 things I want you to take it to your heart. Here is my cheat book with more technical details on the taxonomy of statistical learning, machine learning, and AI. Okay, if you click on this one, it goes to a place. It's going to be a different screen, so I'm going to drag that to this place. You see this one?
Yes.
And I have something like 30 methods there, 27 methods, including reinforcement learning and so on. Okay.
Okay.
So this is a kind of dictionary. You can just take it, review this, keep it with you.
Okay.
That's one thing. The other thing I want to talk to you is that an executive's guide to machine learning, a high-level taxonomy of methods useful for interview. Okay, so let's click on that one and see what we get. So here is that one. So I would like you to read this one. It's beautifully written. How are traditional industries using machine learning to gather fresh business insights? What about outside North America? What were the early foundations of machine learning? What does it take to get started? Okay. What is the top role of top management. And here is that picture.
Okay.
And then this sounds awfully like automation replacing humans in the long run. Are we any nearer to knowing whether machines will replace managers? These are all the questions you will have. So in the long run, there is no need to worry. That's a question. Just read that one. But there is also a guide to machine learning at high level of taxonomy. So this is just a kind of information that they provide. Okay.
Okay.
In terms of learning how machine learning fits into management. Now, here is another one I want you to take a look at it. This is also from McKinsey. I like McKinsey people. Okay, I think this is McKinsey. Wait a minute. Yes, I think it is McKinsey. Yes, it is McKinsey. Okay, an executive's guide to AI. I know it's machine learning. People talk about it. AI people talk about it. Statistical learning people talk about it. So they give their understanding of the ideas, and they really made it very simple. So I would really like you to read this also. Can I take that message that you'll read this and make sense out of it?
Okay, sure.
And they are also talking about what I did. They are also doing it: linear regression, logistic regression, linear quadratic discriminant analysis. I didn't put this one. I'll put it. Decision tree, naive Bayes, support vector machine, random forest, adder boost, gradient boosting method, simple neural network, K-means clustering, Gaussian mixture model, hierarchical clustering, recommender system. We learn a lot of things, and here are some interesting things, how different people contributed to that. Very nice article. I liked it. Okay. And now we are going into, with the machine learning, we are, beating the Lee Sedol, that, the great South Korean, right? Korean player, Go player, who was the world champion. But, Google's AlphaGo beat him. Okay? Not 100%. But what happened was, Google created AlphaZero, next version of AlphaGo. Man, it beat AlphaGo every time, which is kind of, this is the child, right? This is the child, this is the father. The child was beating the father 100% of the time. There is no way AlphaGo can ever be used. The AlphaZero is the one that is going to be used, if at all. If anybody claims that I'm the world champion, okay, come on, let's play with AlphaZero, and you will be beaten. Okay, and that is what the current status. It is in 2017. It's the AlphaZero is constantly learning every day. There is no other way work for AlphaZero to do. Just keeps on playing itself. It knows everything. How to play Go and beat anybody who is willing to play with that. You have zero chance of winning with that, because it was beating AlphaGo, which beat the world champion. So we are at that stage right now, and so it's a fascinating field. And there are a lot of interesting things happening, and there is no going back. Ginny is not going to go back to the
bottle.
Yeah. How are you, Sharanya? Are you hearing me?
Yes, sir. I'm listening, sir.
So read these things. It's very, very important.
Sure, sir.
But what is that? This graph is great. Okay, fine. But how do I apply it in real life, right? Given a problem, how do I apply it? So we are going to start with the decision tree, and then we will talk about random forest, and then boosting algorithms, which is a huge collection of applications. And then we will also talk about these are all boosting, right? And then we'll also talk about neural network. Okay, I will teach you that one. And then the SVM. Okay, I'm going to teach you that one. And then the deep learning, I'm going to teach you that one. Okay, deep learning, image analysis, text analytics, we are going to do that. And then finally, we are going to do reinforcement learning. Okay, this constitutes the machine learning and AI.
Okay.
Now, so let's just take this example, decision tree. Just one single decision tree. Okay. So here is the data set. 12 observations are there. And these are the attributes or variables we have about each of the observation. But what does this observation mean first? Let's understand that. This is 12 data points were collected on the behavior of 12 people when they were visiting different types of restaurants. And we randomly selected 12 observations. Keep it there. There were a lot of observations, but we randomly selected 12 observations. And the first person, when that person went to a restaurant, he went to a French restaurant. That's what this means. Okay? French restaurant. And then it's a high-priced restaurant. And when he went there, it was a it was not a rainy day. Okay? It was not a rainy day. And that French restaurant did not require reservation. I'm sorry, it did require reservation. It is okay. The French restaurant, it was a Friday. He went to a French restaurant. It's a high-priced one. The French restaurant does require reservation. And when he looked at it, when he came, he looked at it. There were some patterns sitting there. Was he hungry at that time? Of course, yes. Was it a Friday? No, it was not a Friday. Was there a bar inside there? No. Is there an alternative restaurant nearby? Yes. These are the situations, and he was told he has to wait, maximum 10 minutes. So far, so good about the story of the data, about the person.
Yes.
Yes, sir.
Okay. But here is what the decision happened. Did he wait or he left? In this case, he did wait.
Yes.
Now you can interpret how the X2 is, right? It's a Thai restaurant. He was told he has to wait 30 to 60 minutes. There is no reservation. There is no rain. It's inexpensive, full of patrons. Was he hungry? True, he was hungry. Was it a Friday? No. Was there a bar? No. Is there an alternative restaurant nearby? Yes. Did he wait? No.
No.
That's what this means. Okay. How about now? 8. Can you say, Sharanya, can you interpret this?
Yes, sir. There was no alternate restaurant next to it, and then there was no bar in it. It was not a Friday, and he was hungry and he had some patience. And
Patrons.
it was
He saw some patrons.
patrons. Oh, okay, sir. Sorry.
That means there are people sitting and eating.
Okay, sir. And then it was a Thai restaurant. So the decision is that he will wait.
He will wait. Okay.
Yes.
You want to read this one, Gaushali? This is also Thai. Let's go to 12. Do you want to interpret this?
I'll take next one, sir, for the next question.
Huh?
I'll answer the next question.
Is this Gaushali talking to me? Okay, never mind. How about Nini? Do you want to say this one, last one?
Yes, sir. So this is a burger place. No waiting. It wasn't raining. It's a cheap place and full of people. Yes, he was hungry, and it is a Friday, and it has a bar, and there are alternate places nearby.
Okay, and did he wait? Of course, he waited.
And yeah, he waited.
The question is, why some people wait, why some people doesn't wait? Can we explain that using these variables? That's what the point is. Okay. Why does it matter? Because if the restaurant can predict, they don't want to lose the business. If somebody cannot wait, go away, they lose a pattern. They don't want to lose that. So they may invent something or do something, I don't know. Maybe they'll give something to eat, small snack, I don't know. Okay. Or they'll give a glass of wine. We don't know. Maybe not wine, it's expensive. Maybe they'll give a snack. They do that, I know, in some restaurants.
Or they can have an outdoor seating.
Outdoor seating. But what I'm saying is now, whatever it is the data. That you have to assume that when we say some pattern, they are seeing outdoor, indoor, some patterns. Even they see full outdoor, indoor, whatever you can imagine, that's okay. The restaurant, whatever the seating they have, it's full. Or it is, some of them are there, none of them are there. 3 categories. When you go to a restaurant, if nobody is there, what is your decision will be, you think? Just one variable.
Maybe it's not good.
I will be discouraged to go inside. Believe me, true.
Maybe it's not good because if no one is there.
Yeah, see, we don't want to go data outside of this. Okay? Maybe it's not good, but that's not what I'm saying is now. Each one of these has an implication in our brain. We make a decision. That's what this one is all about. But only the captured variables are this. Nowhere we are saying whether the food is good or bad, okay? Or how many stars the food getting into. But that's a wonderful variable also. Absolutely. How many stars you have, right? This is the 3 star, this is 2 star, 5 star. Who knows, right? We can add that. Yep. But as long as you understand this problem, you know how to build a decision tree out of this. It doesn't matter how many variables you have, right? Let's do that. How to build a decision tree. But before we go into how to build a decision tree, we want to understand what is called the entropy, because that's what we are going to use to build the decision tree. Okay. So entropy entropy is a measure of uncertainty, also called sometimes a measure of chaos. Okay. But we will call it as a measure of uncertainty. So using the behavior of uncertainty, we will be able to think on how to build algorithm, create a decision tree type algorithm. There are many measurements you can use. This is one of them. Entropy is one of them. First, let's understand what is meant by entropy. Okay. So entropy refers to the number of bits needed to store the information. That means if it is more chaos, you need more bits to store that information. If it is no chaos at all, yes or no, then you have, very simple bit is good enough to, simple bit means we are talking about, a computer, a word in a computer used to be 8 bits, 16 bits, 32 bits. Now it's 64 bits. A word in a computer. Okay, so a bit is the least yes or no, electrical signal, right? Changing the electrical signal, yes or no. So what we are saying is that we want to measure if it is yes or no. It's very clear, right? So you just need you just need no bits at all, no information. There is no uncertainty there. You need to store uncertainty. So you have to be careful here. We are talking about the reverse process here. That's where it is becoming a negative here. Okay. So what we are saying is that if you toss a coin, for example, if it is 0.5, it's a yes or no, it's a 0.5 probability, right? Whether head is 0.5 as well as tail is 0.5, then that is the maximum uncertainty. Is that correct? Because when you have more and more towards either yes or towards no, higher and higher probability, then you have less information there. There is something more information, more uncertainty when you have the highest uncertainty. You need maximum bits to store that information. That's the kind of understanding. That is called entropy. Okay, maximum uncertainty is measured by maximum number of bits needed. Am I making sense? So we want to construct a function. That's where I'm going here. Entropy refers to a function, a mathematical genius information capturing mechanism, which captures the uncertainty in the events. The more the highest probability when you have, there is no uncertainty there. Lowest probability you have no uncertainty. Lowest is 0 or 1. You have no uncertainty here in these extremes. But uncertainty increases as you go more and more towards 0.5. The maximum uncertainty is attained at 0.5. Am I making sense?
Yes, sir.
Okay, cool.
Yes, sir.
Sharanya, good. Go, Shali. So, and how do you measure this mathematically? There is a beautiful, simple expression that is called the minus p times log p base 2 q times plus q times log q base 2. Okay, so p refers to probability of success. That means q refers to probability of failure. Okay, which is 1 minus q. You can say that way also. P log p plus 1 minus p times log 1 minus p. You can say that way too. But it is with respect to base 2 because it's only 2 possible events. And fundamentally, entropy is measured at 2 possible events, and this is how it is measured. So if the probability is, p is equal to 1, so you can put it here. You can actually calculate this. When p is equal to half, it is half times p is half, logarithm of half times with half with respect to base 2, plus half times logarithm of half with respect to base 2. Because if p is half, q is half also. And log 1 any to the base 1 is always 0. Okay, so and also log 1, this one, a logarithm of a divided b is log a minus log b. So log a becomes 0 because it's 1, log b becomes 1 because logarithm anything to the base same base is 1. Logarithm of b to the base b is 1. That is the meaning of logarithm. That's the principles of properties of logarithm. Are you with me? So this becomes 1. Do you agree with me?
Yes, sir.
Yes, sir.
Okay. So
Yes, sir.
but it becomes minus 1 because it's a log. See, this one is logarithm of 1 to the base 2 minus logarithm of 2 to the base 2. Log 1 to the base 2 is 0 because anything log of 1 with any base is 0. Log minus of log 2 base 2 is 1. Okay. In the same way, this is also minus half. This is minus half. This is minus half, and that's why it is 1. Are you with me?
Yes, sir.
So you might be wondering here. I would state this. Okay, one moment, please. We're going to do this. I think there is some typo there. So it should be and there is a minus outside also. That's why it is 1. Okay? Everybody?
Sir.
Understood? Okay.
Yes, sir.
So let's use this definition. This is what is called the entropy. Okay. So information gain is what is called entropy before split minus entropy after we split. That is also called uncertainty reduction. 1 minus entropy x. Okay. We'll come to that. Okay. So when p is equal to half, I already explained this one. But for many multi-class variable with k class, the entropy is like this. We just add these classes. That's all. That's what we have done here. Instead of 2, if it is k, this is what happens. So that's multi-class entropy calculation, and the information gain there is 1 minus of these values. So we can do multi-class also. So let's use these ideas for creating a decision tree for this specific data. This data. Okay, recall all these things. Remember that. Now from here you can see, I'm going to go back to that data. I will take this, we'll just use a couple of examples and then we will extend that idea. Oh, this is how it is done. Okay, we're good. Okay. The question is how to select the best feature for growing a branch in a decision tree. Okay. Use weighted average of events information. Okay. Content. So, are there patterns or not? Let's take a look at the variable, okay? Because I did tell you that my mind says really I will not be, if I don't see a pattern, normal dates of, if I go, especially if I go for a Friday, if I don't see a pattern, I'll be very, very concerned, okay? Something is not right. I don't know what it is, but it doesn't matter. I won't go, most likely. So let's take that variable, right? There are 3 possibilities. No patterns, some patterns are available, and full of patterns. And there are how many cases are there? There are 6 of them. with full of patterns. 1, 2, 3, 4, 5, 6. Okay, that's what this says. This 6, that's what this means. Okay. Now, there are 2 no patterns at all. Is that correct? None is 1 and 2. Agreed? Okay?
Yes.
And the remaining is, some patterns. That's why it is totally, it should come out to be 12. 6 plus 6, 12. So among the 12 observation, I take the 12 observation and then find out how many classes, how many observations are there in the full versus some versus none, and this is what it is. This is what it is. Okay. And let's also consider in the same way the food type. Food type is the following. There is a 2 French. Oh, by the way, I have to differentiate the green and the blue and red. Red means people who did not wait, and green, blue means people who did wait. Okay, so there is no data here. I have all of them are actually did not wait. Here also all of them did not wait. The only uncertain case based on the data is this situation. Okay, only uncertain situation is this. Let's go to the food type. French, I have, for example, 2 of them are there. Is it correct? French, 1 and 2 only. Correct? There are only 2 cases.
Mm-hmm.
Yes, sir.
Yes, sir.
How many toy are there? There are 3 toy. 1, 2, 3, 4 toys. Right? Like that, these are the counts are made to given to you. Toy 4. Out of toy 4 people, how many people are weighted? How many people did not wait? Let's just go and see. 1 did not wait. 1 did wait. 2 did wait. 2 did not wait. That's what this one is. 2,
3 did not wait.
And 2 blue. Sorry?
3 did not wait and 1 waited.
2 did not wait. 2 did wait. Let's
No, 3. I think 3.
Oh, 3. Toy is, one second, let me go. How do I, no. So, 1,
1.
2, I'm sorry.
2. Here
2.
in the fourth.
Right?
True.
2.
Yes, sir,
what about did wait? 1, 2.
1.
2.
That's it, right? 2, 2.
2 and 2.
Yeah. So that's what we have
2.
here. 2 and 2 here. Likewise, you have to interpret, okay?
Okay, sir.
When there is a 50-50 chance of events happening, it doesn't contain any information or does not contain uncertainty reducing information. Uncertainty reducing information. Okay. So for the training set, P is equal to 6, N is equal to 12. P means the number of cases which did wait, right?
Yes, sir.
The calculation X, this is called entropy, right? Let's go to that and apply this 6 over 12, 6 over 12. And we know that 6 over 12 is a half. That's exactly what it is, right? 6 over 12, 6 over 12, 6 over 12, 6 over 12, right? So that's what turned out to be 1 bit. Now, let's go back to this one. So this is how you calculate. So we want to find out which variable should be used to split at the first step. Visually, if you look at the food type, it has equal probability. We are talking about this one. Between, if I consider the comparison between these two, whether I should use this or I should use this, it's very clear, right? Visually, you can, when you look at it, this one by this notation we have created, that every one of the food type has equal chance. So it has no useful discriminatory power. Okay, got it? See, if it is the entropy is maximum here, okay, entropy most uncertain thing, you cannot do much, you cannot discriminate it, it is either way, we cannot discriminate it. But if you have here, you can say discriminate, oh, this is more likely to fall and this is less likely to fall. The more closer and closer you can discriminate it, right? Very easy to discriminate it. So that's what we are saying here, kind of, the information going back and forth between uncertainty and information gain, okay? So if you look at food type, it has equal probability for every one of the food type, and so it has no useful discriminatory information. That means no gain you can achieve. So let's go to patterns here. So it's not a good variable to start with if I compare between these two. So we start with this. So we calculate these values, right? For patterns variable with none class, okay, 0 weighted out of total of 2. 0 weighted after for a total of 2, right? So the probability of happening that event is 2 over 12, and the probability of and this is the case. 0 is, nobody is waiting. Okay, nobody is waiting. This is the other class is 1. On the other hand, for patterns with some class, all weighted. So total of out of 12, the probability is that 4 over 12. The weight of this sample, I'm talking about the weight of this sample, each of the cases is 2 over 12, 4 over 12, 6 over 12. Now, we have to evaluate these values also, right? What is the probability? P is 0 here. Here, P is 6 over 12, right? This is P is 0, but nobody is waiting here. Am I making sense? The total weight to the 12 gives you the weight attached to the entropy, and the entropy itself is calculated by the P value and Q values. This is P is 0 here. Q is 1, okay, that means probability is 1 that they will not wait. And P is here 1 and Q is 0 here, that's what this one is. But here in the third class, it's P is 2 over 6 and the other problem, Q is 4 over 6. Are you with me?
Yes.
And you calculate all these things systematically like this, just using this formula. Using this formula, you get the value, what is called the information gain. That is 1 minus the prior information is equal probability they were likely to be equally likely to be staying or not staying, total entropy, out of which how much information, and then you calculate the entropy due to this variable. That difference is the information gain, and information gain here is 0.541. It's very easy, just apply these values, you'll get it. You can take an Excel sheet and do it if you want. It will work out, okay? Now, if you use the same thing for the type, okay, I calculate it and show it to you again. For each of these, the weights are 2 over 12, 2 over 12, 4 over 12, and 4 over 12. These are the weights, total sample weights are this weighted. This is basically information gain is the previous class uncertainty minus weighted entropies. That's all. Weighted entropies. And the entropy here is for this class is half-half. For this class is half-half. This also half-half, which is 2 over 4, 2 over 4. This class is also 2 over 4, 2 over 4. That's what it is. And if you calculate all this, it will become 0. This is equal to 1, right? This is equal to 1, this is equal to 1, this is equal to 1. But then each of them is a fraction probability. So this becomes, whole thing becomes 1 only. So it becomes 0. So if I compare these two, which variable I have to select as the first, split? Patterns, because there is 0 information gain by using this. Are you with me?
Yes.
Excellent.
Yes, sir.
Now, actually, that's what I have done it using the Excel sheet here.
Sir, I have a small doubt, sir. After we calculate the entropy, it's 0.54, which is almost equal to 1 by 2, no, sir? So,
no.
Will that be a good...
Don't approximate too much. Yeah, it's almost half, but we are not going to say like that, because every little reduction in the uncertainty matters, or every information gain matters. Okay.
Okay, sir.
So because the whole value is between 0 and 1, remember that. Okay, it's not.
Yeah, yes, sir.
100 versus 1 comparison and all. Okay, then you can round it to 0.5 and so on. Okay, am I making sense?
Yes, sir. Yes, sir.
Thank you. So actually, I have it here in the Excel sheet. I showed you that. Really, you can calculate these things yourself, and weighted entropy is 0.459. That turns out to be this is the weighted entropy, so information gain is 0.541 actually, right? 0.541. Okay. So here itself, I should probably show it to you truthfully, but it is 3 decimal one. No, it's 3 decimal is there, but here somehow 2 decimal is there. But if you do it 5.541, but you have to do this for every variable. Wherever you have maximum information gain, you use that as the place to split. Everybody got it?
Yes, sir.
Yes, sir.
So that's what is happening here. We got that one. Patterns is the first variable, and you can do other variables also. This will be the maximum information gain. You will see that. You can calculate that. Okay, and then so there is nothing to split here, because we know for sure if you have no patterns, everybody will go away. If you have some pattern, everybody will stay, but based on the sample. So we have nothing to split there. The only place to split towards the most gained pathway, most information gained pathway is these two. These are all the ones that is coming. So wherever red and green are there, it's all end nodes. It ends, that's it. There is no more further splits needed for the sample we have. Okay. So after that, how many people you have? You have here, right? So when you go to this one, you have only these people that is coming into play, right? The 6 people. And if you take that 6 people, then weight estimate will become the most important thing. Okay, are you with me? You have to do the same thing with the limited people now. So you might be wondering, how am I going to do the second level calculation? So here is the Stack Overflow that explains that. Same thing, but you are going to work with the 6th observation. Okay, so look at this one. How many people liked it? Okay, so take a look at that. They have given an example here how to do the second time if you want. Okay, there's also some other notes I have given you and so on. But you don't know, you can do it yourself also. You know how to do it. With only 6 samples you have to do. Remember that, huh? Because you don't have more than 6 samples here. With that 6 sample, you are going to evaluate what is the next variable. Okay, the next variable is here already solved for you, is that weight estimate. How long you wait is going to play a role. Out of the 6th observation, the greater than 60, is probably only one observation. They don't wait. So it's just gone. If it is more than 60 minutes, who will stay, right? So that node ends with that one observation. And how do we know that? Let's go back and check. These observations we are talking about here. One moment. Here we are talking about full. Okay, so among these full, how many observations are greater than 60? There is only one observation. That's a fail. Did not wait. Do you see this one, what I'm saying?
Yes, sir.
Yeah. So let me put maybe color it differently. Oh my. Some more trick will show it better. Gradient picture, I don't know how to do it. I know there's a way to do that. It doesn't allow me. There's a way to fill that gradient so that you can see through, right? Edit. I don't know. Yeah. Sometimes it comes through, but here, I don't know why it doesn't come through. I want to see through type. Let me see. One more time. Okay, I think it is here. Transparency, okay. You see that one? I don't know whether you could see the color now that much, but I can make it more full colors. Yeah. So if I go to 70, it will look better, I think. I don't know. Can you see that color? Light color is there. Okay. I can make it more and so on. Okay. Let me do one more try. More full color. 50 maybe. I think 50 is better. Okay. I think you can see that. There's only one observation. That's why it ends there. Okay. My point is it ends there. But then the remaining observations, 5 observations are, going to be used to differentiate. Oh, if it is 32, there is an information gain available. Totally, there is more information gain available as the next variable for the weight estimate. And then after that, each of these classes, this is one observation, this is one observation, there is, remaining 4 observations are split between these two. Okay. Accordingly, we get, alternate, is there an alternate restaurant available or not? And then if you are going to wait only 10 to 30 minutes, it depends on whether you are hungry or not. Okay. But if it is 30 to 40 minutes, 60 minutes, then you are thinking, oh, maybe I should go to an alternate restaurant nearby. Okay. So that's the way we are, we are doing the full split. Is everybody good on this, what I'm talking to you?
Yes, sir.
There's a lot of work, if you want, you can sit and calculate all these things, but that's how it is done. Okay. And so I was talking to, there is how to do this. And I have some, actually I present it to corporate offices where actually I use R to do the second level calculation. Okay. I can give you that also, that program, not program, it is just a presentation deck. Okay. That's a different presentation deck because I have to do the whole machine learning, ML, AI topics, supervised algorithm, unsupervised, all those things, in a very compact form, in a short time and so on. So I just show them, using R, you can do that. Now, that is how the decision tree is built. Do you think you can, given enough time, do you think you can build it?
Sure.
Good.
Yes,
I like that, Nini. How about Sharanya?
Yes, sir. I think it's possible.
We can build it.
How about Gaushali?
Yes, sir, we can build it.
I'm going to shift audio to something else.
Can you hear me, sir?
No, I hear you, but it's not that great. One moment, and it's not your problem though, so don't worry about it. I'm going to see whether I can change the audio here. Maybe not. Okay, so I think I have here audio. One moment, please. I don't want this. I want speaker. Okay, now say hello.
Hello, sir.
No, it's not coming well. Why is that? Not that loud. One moment. Yeah, it is too low. How about now? Say hello.
Hello, sir.
Oh, there you go. Perfect. Beautiful voice. Okay. Now, so the beauty of decision tree is that when the decision tree was built initially, you can see this is a classic example. Okay. And then they also did, some other method that is called random forest. So what is the difference between decision tree and the random forest? Decision tree is also called strong learner. Okay, that means decision trees are in general learners, and single decision tree is considered random forest is a large collection of small trees. If you ask somebody asks you a question, what is meant by random forest? That's a best simple answer. It's a large collection of small trees, small size trees. On the other hand, decision tree is one large tree. This is a very simple way of explaining what is a decision tree versus random forest. The problem is, once a variable is selected to build the branch, the path of the branch is fixed. Okay? Once the branch is, built, the path of the branch is fixed. If a smaller information gain variable relatively has a bigger impact in prediction via future branches, that opportunity is lost in the big decision tree. So, in order to address this problem, what random forest does is you know what? We don't need to build one decision tree. We'll make lots of decision trees and make it into a forest where most of the trees are, most of the branches are. We'll give a lot of weight for that. Does that make sense?
Yes, sir.
Okay. How about you, Nani? I'm sorry, Nini? Nani.
Yes, sir.
Okay, thank you very much. So, so that is the idea of random forest. What inspired is that, if I take small trees and then put them together, then if I map it where I have a lot of greenery, that means that's a place of decision, powerful decision nodes. And this place will have such nodes, lot of little trees here, 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 lot of little trees here. They're like that, okay? And that's what random forest is doing. And so we want to compare, that's one thing, okay? The method of building multiple trees in this fashion by using fixed number of random collection of variables results in a collection of trees. So how do you build random forest? You fix the number of variables to enter, maybe even as simple as one variable to enter. That's called stump. Or it could be a couple of variables, 2, 3 variables, 4 variables, not beyond. More and more you add, you are going towards one big decision tree. You don't want that. Just, that's why you have to use small number of variables, and then you take samples. Constantly you select. So you sample on the column, which is the variables. You sample on the rows, which is the observation. And so many samples you can create. That's why you get a forest. And so many trees you can build because of that. Okay, so random forest is based. It's on the it is built on the basis of collection of random subset of variables and also called random subset of observations. So that's why random forest beats it, because we are optimizing it by randomly selecting many times. And then we are also randomly selecting on the row side many times the observations, right? So those two are parameters in building a random forest. You will see later on. Okay. So we also called, so I told you that there is randomization on the variable side, column side. There is also randomization on the split of training and testing is also called Bootstrap method. So every time we take a sample, we split at that time. Take for the subsample, we split training and testing. So you don't need a separate testing in random forest. And this is called Bootstrap aggregating method, also called bagging. So in bagging, what happens? You are actually taking a sample, training and testing. So you train the model and test the model, and then find out its performance. And then you take another sample, you do the same thing, and then you average this performance. That's what the bagging method is about, and you will get that answer. You don't need a valid cross-validation for random forest. That's the point. Am I getting across? And what is meant by cross-validation? You didn't have a chance probably, Nini, So it is, let me open a file and then show it to you, that part for you, because you didn't go through. I spoke that in PA1, that is, unsupervised algorithm, okay? So let me tell you that. It's basically rotating the sample, okay? Given a total sample, you rotate that, okay? Cross-validation. You don't need that in the case of, so this is what it is, right? So what we are saying is that you have the data, okay? You keep some test sample you can, okay? Sometimes you don't need to do it. It's okay if you don't do it also, okay? But people recommend that you set aside. I say it's okay, because if the sample is systematically well represented, you will get the same result here. Whether whatever you get here, you should get it here, because cross-validation, takes care of the problems and the variations in samples. So what happens, if you have 1,000 sample here or 10,000 sample here, then you split it into, let's say, this is called 5-fold cross-validation. 5-fold cross-validation. You take 20% and keep it for validation, remaining 80% you the model, that is model 1. And then you take the same data, split it a different 20%, mutually exclusive different 20%, and the remaining part as training, and then validate it on this one. That is model 2. Now in model 3, you do the same thing. 5-fold means 5 models you get, right? Because you are folding 5 different ways you are taking the sample here. It's a different validation data set compared to the previous 2. It's a mutually exclusive, compared to the previous 2, and the remaining will be used as training, and this is testing, like that. this is training, this testing, and this is training and this testing. So the sampling variation issues will be addressed very nicely, easily by cross-validation. In fact, this is a gold standard. If somebody asks you what is the best way of doing your testing, building a model, training a model, and doing the validation, you have to say cross-validation. Okay?
Okay.
That's the best. But
what about overfitting, sir?
This will avoid overfitting. That's what I'm saying. Because, there are overfitting can happen due to many reasons. Okay. One reason is due to the incorrect sample selection. See, if you do only once, it is possible that this 20% is, nicely goes well with the, the overfit model. So the overfitting can happen because you over-parameterize it. I will come to that. Okay. The over-parameterization is handled here in the test sample. Okay. And over-parameterization is also, if it is the parameterization depends on the sample, that's where this will eliminate that. But I come back to this one. I say that it is better to set aside the tests.
Okay.
Okay. That's a good question. Okay, thanks a lot. Sharanya, are you with me? Gaushal, are you with me?
Yes, sir.
You understood our question, how I answered it, right?
Yes, sir.
What this eliminates is it eliminates the sampling variation related problem. It doesn't directly eliminate the over-parameterization problem. Okay. And that's why you need the test also. So I think somewhere I did say something like this. Maybe I'll correct me if I haven't powerfully said what I'm saying now. Okay. So that is the cross-validation, and that's what we are talking about here. When I said that you don't need a cross-validation in the case of random forest. That's my point. Okay. And here Breiman compares 10 different data sets, and then he is comparing which model beats, whether it is random forest or single decision tree. Okay. And these are mean square error. Okay. These are mean square error. The blue, which is random forest, mean square error, is systematically below the single decision tree mean square error. So which is better?
Random forest.
Yes, random forest. Are you with me, Gaushali and
Yes, sir.
Okay, excellent.
Yes, sir.
Yeah, so it's a very powerful graph. See that this is what visualization is about, right? In one powerful graph, it gives you the powerful conclusion. That's why.
Now look at the shuttle X103. That's terrible.
Yes, you're right. For some reason, single decision tree is pretty bad. You're right.
Yes, sir.
But we don't want to talk about just one performance always. Just take the message of overall. It's always below, so uniformly below. That's the most important. Okay? We don't know really why it happened here. I really don't know also. Okay? But this is a comparison coming from Breiman. He made a very important, powerful paper called Statistical Modeling the Two Cultures. This is where he is a statistician, and he said we all have to change. Man, things are coming. We can't do the usual statistics anymore. That's what this is about. Among statisticians, there are two cultures. One who believes in, this kind of data science, where random forest, they never thought about random forest. Statisticians, okay? They went up to single decision tree, that's the end of it, right? But obviously you can see that, even single decision tree, many people say it's not a statistical method. Why? But some people do say, in fact, there was an argument in one meeting. I have to tell them, look, single decision tree, it doesn't matter whatever you use the measurement to split, statisticians know it. In the beginning it used to be chi-square. It's called CHAID, chi-square aided.
Chi-square, yes, sir.
Yeah, it used to be called CHAID, all kinds of names, aid, CHAID, BAID, all those things came, right? But the point is, it's because it's chi-square, for me it is statistical method. Okay? But anyway, so that people will talk, whatever they feel, it's interesting for them. So let's take a simple example. Go to R. Go to R. If you all of you, can we do that? A little bit of work.
Sure, sir.
R Studio. Or should we take a break? Okay, I think you all need break now or not? Because in another 45 minutes we'll be done.
No, sir, no need of break. We continue.
What do you feel, Nini? I'm supposed to give every hour 5 minutes break. That's a legal requirement, maybe. Okay.
I'm okay.
All right. So you can go to. Let's go to. You're able to see my screen. Let me see. I think it's probably I can move it here. Okay, going back there. Okay, yeah.
So can you please share the link?
Which link?
The R Studio, you ask us to open the R Studio.
No, that's what
You have the
you're talking about. This one, right? This is what I'm showing, right?
Yeah.
Is that what you're
Okay.
asking?
Yes, sir.
Okay, it's there. Okay, right now I'm there. Okay. All right. So let's take library mass. I think package with library mass will be there. Okay. Let us see. Yeah, library mass. Let's just copy and paste that. Okay. And then data master. All right. There is no package called random forest. Okay. I didn't do the. Don't have random forest. I'll have to install it. No, it's not this. So. Random forest. Install. So let me take that into the library. So I have the data right now. So Boston. See, data is already there, right? So let's call structure Boston. So this is the data that Boston has. It's a Boston housing data. Okay. There are 506 observations with 14 variables, and it talks about the value of the house, median value of the house. Okay. It is in, let's say, tens of thousands of dollars or $100,000. Let me see what it says. Okay. So we are talking about median value. Yeah, MEDV means median value in thousands of dollars. Okay. So it's old data, and it says let's talk about Ted Boston. Okay. So the first house is value is median value. It's the last variable, right? So $24,000. It's old data. Okay? It's $24,000. Maybe a Boston neighborhood, some suburban area. And the crime refers to the crime rate per 1,000 or 10,000, something like that. Okay, let me see that. What it says. Crime is per capita crime. Oh, it's per capita crime. It's not per 1,000 per capita. Whatever the total number of people are there, how many crimes happen around the name and that particular neighborhood. It's all different neighborhoods. Okay, different neighborhoods. And this DIS means distance to employment centers. Okay, RAD means accessibility to radial highways. ZN means person land zoned for lots. Okay. INDUS means percent non-retail business industries. That's what it means. Non-retail business. Tax means property tax per $10,000. Okay, let's see what it is. Tax means this is per $10,000, $296 tax. Okay, per $10,000. So this will be, what is the tax for this one? 2.4 times 296, which is approximately 2.5, 2.5. That means for 500, 600, very close to 650. That's what this particular house is paying. Are you with me?
Yes, sir.
Okay.
Yes, sir.
And then PT refers to people-teacher ratio. CHAS means whether the house is on the Charles River or not, because if it is on Charles River, it will have a higher price. And then NOx means nitrogen oxide concentration, which is a pollution issue. What is the percentage of blacks are there? So there's some calculation going on there. Percent black minus 63 times 1/5, 2 times 2/10. The average number of rooms is RM. LSTAT means lower status peak population percentage. Age refers to person built before. This is the age of the house. Person built before 1940 in the neighborhood. Is everybody good on this one?
Yes.
Cool.
Yes, sir.
So we have the data. So here is the command. Very simple. See, this is the beauty of it. This is why it's called low code, right? Low code, no code, all those things are coming. So if you want to know the command, know about what is random forest, you just put the question mark random forest with uppercase F, packages uppercase F. And it will give you details for you. And let's do something. Actually, why don't we do that? Question mark. So you have some notes here, all these parameters to fix and so on and so forth. So there is so much work, you can also read about all these things. But I just want to show you the taste of this now, right? How do you judge the model, all those things quickly? And then you can take a 5-minute break. So what we are saying is that you have to define what is X and what is Y. So Y is the 14th variable, the last variable, which is the median home value. Okay. All the rest of the variables are all 1 to 13 is our explanatory variables. So we model Y as a function of X. That's our random forest. Okay. So that's what we are doing here. Random forest is, you just have to say what is X variable, what is Y variable. So we don't know. We actually define what is X and Y, because that's how we know. You have to note it in the command. So random forest, let's just put here also. Random forest is equal to I didn't do the X and Y. So first I have to define the X and Y. Y is equal to Boston, comma 14. Okay. And then X equal to Boston, comma 1 to 13. Is everybody good? Is everybody good?
Sir.
Yes, sir.
Now you do the random forest. Okay, X comma Y. Done. Okay. And there are some default things are there. That is, default thing is use 500 trees. And number of variables tried is 4 at each split. These are default values. If you just give like this, it takes the default values. And percent variance explained is 88.43%. You remember, percent variance explained is all what we are interested in the case of continuous variable. What is the continuous variable here that we are modeling? What is the continuous variable?
Median price.
Median price, median value. We call it as value. Okay, median value. That's what we are building. It's a continuous variable. If you build a regression on that, you are talking about percent variance explained, right? Adjusted R square. That is what it is. It's a kind of pseudo adjusted R square. Okay, but it has the concept of percentage explained. Get it? And then mean squared error residual. You also want to know how much mean of the error, squared residuals are, because it tells you the more the residuals are, the bad the models are, right? So these are some of the basic things you will get in a random forest. You can control the random forest with so many of these parameters. Now, let's go back to one more thing. I want to plot and show it to you. Plot the predicted RF for the whatever the data it used, right? Predicted RF with respect to Y. that will give you the predicted RF with respect to IA is this one, right? Predicted RF. Ab line is this one. Predicted RF. New data is the X, comma Y. Okay. So this is what the plot of predicted RF comma Y is here. Do you see what I'm talking? This is predicted. This is the actual. Are you with me? And if it is perfect prediction, it should lie on this line. Do you agree with me?
Yes, sir.
Yes.
Yes, sir.
So these are all not really good estimates, no? So it's somewhere here, actual values. When actual value is 30, predicted value is, actual value is 30, the predicted value is, no, I can't say go like that. This value refers actual value is 50, predicted value is 25. That's what this means.
Value is 20.
Right?
Mhm.
Okay.
Yes, sir.
And you can interpret like that. But if this is for the whole model using the whole data, whatever we get, right? But I can, if I'm going to use, okay, the new data is just only a specific data set. If I use a very specific data, new data is X, okay? Then, see, when you build the model, you can use any new data set, but I'm using the same data set, right? So if I use the same data set, then I should get less variance, right? So that's why it looks more in tune with the prediction, seems more in tune with the actual data here. But here you take the sample so many times. Every time you are taking the sample, on the row side, and then you are predicting the value, you are taking the average of the values, average predicted value, and so on. That's why here a lot more. But here, very, very specific data you take, and then just for that data set only, you use the predicted value versus the actual value. It looks pretty good, right? Much better than this one. That's all I'm saying. But this is what you get in real life. When you apply, when you use random forest, you want to check how good it is. You want to see that the points are lying on this line. It won't lie perfectly on that line. Okay, I'm just telling you. Are you with me, everybody?
Yes, sir.
Okay. So why don't you take 5 minutes break and then let's finish some more. 5 minutes break.
Sure.
Okay, sir.
Thank you.
Thank you, sir.
Hello. Hello. Are you there, folks?
Hello, sir.
Okay, welcome.
Yes.
Thank you. So, I have been recording anyway. I didn't pause this, so it's okay. So, the one of the important thing is they complain about these modern methods, data science methods, like especially the machine learning methods and AI, is that the models are not interpretable. That's a serious concern. Okay, it's a serious complaint, but I want to show you that it's not totally not interpretable, but still it is not enough. That I agree. Okay, so there are methods to do that, and we will see whether we can address that. What is called the interpretability of machine learning model. But here is a small attempt in that direction. Okay, so if you say when you are able to interpret which variable is most important, in terms of importance of variables, here is the method that you can use. Random forest, x comma y, importance equal to true. If you do that, and that is stored in the RF, okay, with the model is built, and also the variable importance is stored in this one RF. Okay, so if you go here, we can do that here also. RF is equal to random forest x comma y, importance is equal to true. Okay, you always need to do this, because people really want to ask, tell me what are the important variables, when you build a model, right? So, and it provides a way out. So now it is done. Let's see what are the members of this object RFS. Okay, it has all these things: forest, importance, yes, standard deviation, and so on. All these things are there, but I have shown only about the forest information, and now I'm going to show information about the importance of the variable. So let's say the command here is now just var importance plot RF. Okay, that's all you have to say. Okay, var importance var im RF. So here you have it here. There are two ways, there are two concepts called the mean square error, increase in mean square error, and increase in node purity. Okay, so what it says, there are two different measures you can use it. Node increase purity, and and what is called the MSE. It's okay if you just use the MSE. Don't worry about it. We are saying that the number of rooms matters. That makes sense, isn't it? The more the number of rooms, the price is going to be higher, right?
Yes.
And then the LSTAT. LSTAT means what? Let's see. LSTAT means this. Percent lower status population. Okay. Percent lower status population is the next important variable. If there are lower status variable, price will be low, because there are associated problems associated with that. We can't help it. So that is the next important variable, and then the pollution, and then distance to the employment, and the crime. These are the top variables. Okay, there is some difference between this and this. You can see. Okay, so just use this one. I would say use this one to explain your model. Good. Percent increase MSE. So that gives an idea about variable importance. Okay, so which is very important for interpreting the model, but it is not what all the kinds of interpretation you have usually in linear regression. Linear regression is a beautiful, simple model, and even nonlinear, the generalized linear models, nonlinear regression, are also interpretable. They are all interpretable. Remember that. They know what is the contribution effect of a particular variable. They know, if you add 1 unit of X, what happens to Y. This kind of interpretation you can give. Okay, you can give confidence interval, all kinds of things. People are very comfortable with that. And that level of interpretability is still not there for machine learning and AI models. But if you talk to the machine learning expert, they'll say, I don't care about it. No, it is predicting well or not. That's what matters to me at the individual experimental level. So their argument is like that, this people argument is, well, if it is, there is something science that, humans can understand and replicate it and appreciate it and believe in it, then you need to have an interpretable model. But, of late, more and more things are happening there. Even machine learning, we have what is called Shapley values to interpret the variable importance, however complex the random forests are, however complex the neural nets are, and so on. Okay. So that is that's the minimum, level of some kind of a comfort level that we can give to people by using var in plot. That is for random forest. Well, the thing is, the problem is that the random forest can become a biased model. Okay. And also potentially also it takes a long time. So the question then is, can I optimize the process? Can I optimize the process where I am directly going to the solution without going around all over? Okay, point one. Or I might get stuck somewhere, that might happen in random forest. That is one thing. So that is go to the minimum most error, prediction error directly. How can we do that for random forest? Because we are building so many trees and then combine them, right? That's the problem, isn't it? Am I making sense? How can we go directly to the, directly to the minimum most error, predictive error? Because that is not the
Yes, sir.
strategy. I'm sorry?
No, sir. I
No.
didn't again.
That is not the strategy there in the random forest. The random forest is a very simple strategy. Build all small models and then combine them. That is what the strategy is. It is not directly connected to how do I, collect the specific collection of trees in the random forest for which it is leading me to the minimum error in the prediction. That is not an inbuilt strategy. Okay? So question is, can I build that strategy in selecting the random forest members, the trees, in selecting the trees? Am I making sense? That is the question that is answered by boosting. We are boosting at every stage when we build a split. We are boosting the performance by selecting, by reusing the observations which are misclassified, and then making sure that among the misclassified observation, what is the next among the misclassified observation? What is the next variable that explains best? It is different from the previous way of splitting. Do you understand what I'm saying?
Yes, sir.
Meaning?
Yes, sir.
Yes, sir.
Yeah, good, excellent. Because if you capture all that one more time, I'm going to say, at every stage when a split is happening, next stage, based on the previous split, we identify which of them are misclassified, right? Take that misclassified observation. Next time, you make sure that the next time the misclassified observation is maximally correctly identified. Again, you are going to make mistakes. So again, next level, you take the misclassified observation and select that variable that will maximize the correct classification. That kind of systematic way is called the boosting the process of accuracy. Boosting the process of accuracy. And that's what boosting is all about. And I'm going to teach you about boosting using what is called AdaBoost. There are many boosting methods, but AdaBoost is the first one that was introduced by Jo Fruin and Robert Shapiro. I won't be surprised if this guy gets a Nobel Prize because he's now working on economics. He finished this problem in 1999. Last 40 years, he has been working in economics. So this is what happens, right? If you're a brilliant person. So I'm going to introduce you to this boosting method. So here is the example document, example samples that I'm going to work on. Okay. Wait a minute. I think something is it missing? Wait.
So, sir, in our script,
Yeah.
boosting is already built in, or no?
If you ask for random forest, no. You have to ask for boosted random forest. So that is called GBM, generalized boosted GBM boosting method.
Okay.
No, gradient boosting method, generalized gradient boosting method. So the gradient is the pathway that is going down towards the least accuracy. Okay, that's the gradient.
Okay.
So we boost that gradient. So it's called gradient boosting method. Okay, you have to use GBM. In GBM, you can build a forest that will be boosted random forest.
Okay.
Okay. So I have something is not correct here. XGBoost, something has happened not correct here because some slide is missing here. Okay, that's fine for now. Let me, okay, maybe it is here. If you click on this, it will come. Let's see. Yeah, I think so. Okay, there you go. Gosh, it's a long time I touched that file. That's why I had trouble locating this file also. Okay, so boosting way is a way of improving accuracy. Conceptual steps are performed iterative search to locate the regions that are more difficult to predict. And as we move through the iterative process, each iteration penalizes inaccurate predictions for next step to do a better job. So you put more penalty for those misclassified observations in the previous step. Okay. Then, those are difficult to predict. So you put more penalty for specifically item by item, increase the penalty. And by doing that method, you will make sure that your algorithm concentrates on those misclassified observations to do a better job. Am I making sense?
Yes, sir.
It's an amazing strategy. See, they say, let's say out of 10 observations, 5 of them are misclassified. So now you give a lot of penalty. If you misclassify these 5 observations next time, I'm going to penalize a lot of error on you. Then the algorithm will try to take care of that as a first priority. No, I don't want to, because they are being guided to reduce error, right? So they will really, now the algorithm will align itself to make sure that the highly weighted observation for penalty are being addressed better. That is what the idea of this method is. Okay, let me explain what I mean by that, then you will know. Okay, so let me go that. I lost it again. Okay, so here are 10 points. Okay, these are 10 points. These are 10 points, right? And these 10 points. First point is 2 on the this is the x1 axis. This is the x2 axis. Let's say, if x1 is 2 and x2 is 3, then that class is also a plus class. Okay, that sample is like that. X1 is 2, x2 is 3, and the class is plus. On the other hand, x1 is 3, x2 is 2 is minus class. Okay, these are 10 observations here. So what we want is that we want the algorithm to separate out like this, because this is the best separation where 100% correctly identified plus 100% correctly negatives are identified. Are you with me?
Yes, sir.
So if I have built an algorithm that that builds this kind of line combinations. This is one line and combined with this line, segment line, and this line, segment line. Then if I combine all these 3 segments of lines, that will be the discriminator for me to discriminate plus versus minus. Agreed? Everybody?
Yes.
Yes, sir.
Excellent. That is what we are going to do. So how do we do that? And remember this statement I made. Whatever is misclassified, I'm going to give you more weight. And we are going to do that. Okay, so think about this. So the first time I use this, on the x-axis side, what is the best discriminator? I just say on the x-axis side. Okay, I say, I start with the pluses. So okay, I'll put the h1. This is called hypothesis in boosting. Okay, this line separate these 2 perfectly well, 100%. But then, I have misclassified pluses here. Agreed? And it also correctly identifies all negatives. So 70% of them are accurately identified. Are you with me? But 30% of the observations, which are all pluses, are misidentified. Are you with me?
Yes.
Okay.
Yes, sir.
Now what I'm saying is I'm going to make these guys like ghosts, big ghosts, right? This is what it is, but then I'm going to make it bigger. I'm giving more penalty. If you misclassify, next time I'm going to find out another decision rule, which is same as saying decision tree. Okay, decision rule. I'm going to make another decision rule. This is one decision rule. I'm going to create another decision rule. But next time when I do, these guys should not be misclassified. I want such a discussion. That's how will I do that? So I'm going to give a lot of weight for them. So my search will look for that kind of decision rule that first and foremost, it will do a good job of this. Having identified this one, this line, I want to identify this, in this side or this side. I have another independent axis, this one. Either one is okay. So what is the best way? Because this is already exhausted. I have already done 7 of them accurately with this line, right? This line, I have already identified 7 of them accurately. 5 negatives, 2 positives. But the problem is these pluses. So in this, I have used up all the things. Can I do anything here which will correctly identify in association with this? Isn't it this line here that will do?
Mm-hmm.
Or this line. Also you can do, the other possibilities you can do this line, isn't it?
Yes.
If you do this, all the pluses will be identified correctly, but only 2 of them will be, negatives will be identified correctly, but 3 negatives will be, incorrectly identified. Correct?
Yes.
So that is what we are going to do. So we go, in the second search, we have this line, and that's exactly what happened. So because I got so much weight here, what does that mean? That means I have 5 observations, but their power is more than 5 units. And so they get priority. So this is the next best possible line that will discriminate this observation. But then, in this case, we know that, this is correctly identified. In the previous line, I should really put, this line also, that it's hidden there. It's, we shouldn't forget that. We already achieved that part, right?
Mm-hmm.
Hidden here. 1 second. What is hidden there? I'll make it bigger. Okay, and it's hidden. To say it is hidden, again, another trick I'm going to use, that is this one. Okay, it is already hidden there, right? It's done. That's what I mean by hidden. It's already done there. Now, by using this, all this got correctly identified, but I already know that with this line, I have already correctly identified this one, I already correctly identified this one. But what happens, because I brought this one here, this needs to be, how am I going to combine this and this? Somehow I have to combine this and this to get, to make sure that, these are also properly identified. It is impossible to do that. So now I exhausted this whole axis. I'm going to search here on this side. So what I need to do is that I'm going to give a lot of weight here, these 3 things. And what is the line here that will, generate this 3 points absolutely correctly? And that is what this line will be, isn't it? So that line will be on this axis now, right? I have come to this axis, this line. Agreed?
Yes.
But interesting.
Yes, sir.
Yes, sir.
Thank you. But the interesting thing is the following. I'm sorry. Interesting thing is the following, that this one is, kind of, this is what we want to measure. But I got 3 lines. If I can break these 3 lines and combine them together, I have done my job. Am I correct? Because what it says is that up to this, I have to go here, and then I have to combine from here to here, this line, and then from here to here, this line. Am I making sense?
Yes.
Yes, sir.
Yes, sir.
How do we make mathematics to do that for us? This is very strange looking operation, isn't it? Brilliant people have designed these ideas. That's what I'm going to share with you now. Okay, are you with me? It's amazing.
Yes, sir.
Yes, sir.
So what we are saying here is, let me go back and see whatever I have here. Okay. So this is the mathematics. It looks like, this is strange, but this is how, it is written. That is, there is a weight that we have to give here. We will find out how to calculate that weight. That's our job to do. There is a weight we have to calculate here. You take the 0.42 weight times this hypothesis, whatever this H1 is. Okay, H1 hypothesis. That is this line basically. H1 refers to this line. Also they call hypothesis. Okay, the first hypothesis plus 0.65 times. That's what the weights are. When you give that kind of weight, 0.65, then you get, this line. And then when you give the remaining observation 0.92, you get this line. Are you with me? And I'm going to prove it to you, those things. How the heck in the world, people have figured out all these things. I'm going to show it to you, right? But this is what they call the sign function. You combine with that sign function, that is, give weight for all the things under the H1 hypothesis. With the weight is 0.42, and this is some mathematical calculation. I'll let show it to you. Brilliant answer, okay? And again, next level, you get weight is 0.65 the remaining observation, and that's what this gives. This one, these are all connected. This line is connected to this weight, okay? And the remaining observation you give, 0.92, and that generates this line. And if you combine all these things, that's what this H final is. These combinations is what these lines are. That's mathematics. Okay? Are you with me so far?
Yes,
You might
sir.
be wondering how I'm going to do these things. These guys are doing all these things. I cannot understand this and that. But overall, do you agree, understand what I'm talking?
Yes, sir. We'll understand.
Okay, Nini? It's difficult, but don't worry about it. You have to look at it 10,000 times, who knows, or 10 times. But the point is not. They also looked at it 10 times, okay? I mean, brilliance doesn't come just because somebody is born brilliant. You apply your mind again and again and again. That's all. That's the only way. I'm seriously telling you, everybody. Okay? But I'm going to show it to you how to calculate this. That's where your learning comes, right? Not yet. It's not over. There is more interesting things are coming. But it will be over with this one. Okay, see, the final line is sine function of alpha t times ht. These are the functions, right? These are the lines, linear component of those functions, those lines. How do we get alpha t? That's what we are going to find out. Okay, alpha t is really 1/2 logarithm of 1 minus epsilon t error. 1 minus epsilon, that's an error divided by epsilon. The same, the weights. These weights are adaptive weights. That's why we call add a boost. And what is the error? Error is basically the probability that at the ith step, there are 3 steps here, right? The ith step, the d value, that is the distribution values. Okay, the distribution values, that's where the weights are coming. The distribution values, with at the step t, what is the probability that, it is misclassified. So the error of misclassification is used here in this ratio format. The error of the misclassification is used in this ratio format, 1 minus epsilon t divided by epsilon t, logarithm of that, and half of that is your alpha t. And that is the weight. You have to boost it or deboost it. And that is what this is happening here. If exponential of that alpha t is boosting the weights whenever it is misclassified, whenever the hypothesis misclassifies the observation. Are you with me? This is called misclassified observation. For the misclassified observation, the weight you give is e power this alpha t. That alpha t is the boosting parameter, and it is boosted by that exponential function. And here it is a deboosting is happening. For those which are correctly identified, you are reducing the weight. You are taking weight from there to the misclassified observation. That's what this one is. And now what is this one? This is basically coming from the distribution. So if you have 10 observations, the first initial weights are 1/10, 1/10, 1/10. That's what this one is. But then it gets changed. It gets changed by what? It gets changed at the next step. It gets changed based on the previous step distribution weights. And those distribution weights are boosted and deboosted based on whether the given in the hypothesis, whether the observation is misclassified or correctly classified. and we have to normalize that. This is what normalization is. This is the probability distribution, and these are the errors you get, and the errors are errors are used to calculate the weights, hypothesis weights, and based on the hypothesis, and boosting and deboosting is done, and these are normalized, and that's what this one is about. Okay, normalized means make sure that the attributed weights are coming back to 1, because it's all probability weights. So it has to come back to 1. That's why we are normalizing it. So there's a way to calculate Z also. So, and then when we finish this one, you combine all those such functions, such lines. That's what it says. You combine all those things, you get the answer. That is called boosting. So we are going to go through that with the actual data we talked about, right? Remember that 10 points. I'm taking those 10 points here. Are you with me? The first point is it's a plus 1 and 5. X1 is 1, X2 is 5. You can go and you can check that one here, right? Oh no, even here it's okay. So X1 is 5 and Y1 is, what is the value? Second. Remember one of the values. It is the same data. It is the same data. I'm taking it there. Okay. X1 is 2. X2 is 3. Okay. Let's see. X1 is 2. X2 is 3 plus. You see that what I'm talking? It's the same data.
Yes, sir.
We are arranging it like this. Now we are going to do the calculation. Initial probabilities are all equally weighted. But then we are going to change this weight based on whatever is misclassified data are. But for the first hypothesis, we know that these are the 3 observations misclassified.
Okay.
Okay, these are 3 observations which are misclassified for the first observation. So I'm going to boost the weights here. This weights means basically the distribution, probability distribution will be boosted here. Where is it getting the strength? It is taking away these probabilities from 0.1, 0.1, 0.1, 0.1. You take 0.03, 0.03, 0.03, 0.03. Here also you take 0.03 and then here 0.03. This is 0.03, 0.03, 0.03. Okay, because these are all correctly classified. You don't have to give too much weight for them. I need to give next time. I need to give more weight to those observations which are misclassified, and these are the misclassified observations.
Okay.
And we are boosting it here now. How did we boost this one? I told you e power minus alpha, e power plus alpha is boosted up, e power minus alpha is boosted down. Okay. And where is the alphas are coming? It is the normalized value. Alpha is calculated by half logarithm 1 minus error divided by error. You remember that one? Half logarithm 1 minus error divided by error. Do you remember that one? Let me.
Yes.
Yeah, okay.
Yes, sir. Yes.
So that is what this alpha 1 is. Okay. Alpha 1 is half logarithm of 1 minus 0.3 divided by 0.3. That's what this one is. I'm going to show it to you actually, in the Excel sheet also. That's why this Excel sheet is coming out. But I'm right now giving you the strategy here. Okay. And so with that, you can, using this, you redistributed these values. You needed this. And then after you redistributed this, you need to normalize that. That normalization coefficient is because if you add these things, it won't be initially 1. But if you get 0.92, but if you divide 0.92, there's something else actually. In fact, I think it is 0.15. So let me stop here and go back here because it's more real now. I'm going to show it to you with this one. Okay. Let me show it to you with the calculation here. Are you able to see this one? I don't know. Maybe small.
A little small.
Yeah. 1 second. 1 second. How am I going to show it to you as big? Okay, maybe here. Okay, a little bit. Okay. How about now?
Yes.
So here, let me walk you through, because I can walk you through with actual calculation there. Those calculations are hidden there. Now, if you look at this one, please take a look at this one. Okay. And these are the same points. These are the pluses, 5 pluses, 5 minuses. These are a 0.1, 0.1, 0.1, 1, right? This is the probability distribution. We are going to change these weights based on whether it is misclassified or not. For the H1, these are the observations which are misclassified. Okay, are you with me?
Yes.
Because
Yes, sir.
classified, you remember 3 of them are misclassified, isn't it?
Yes.
Okay.
Yes, sir.
So their error is 0.1. Right now their error is 0.1, right? This point is not enough. Okay. And we are saying that we are going to take away 0.3, 0.3, 0.3, 0.3 here, 0.3 here, 0.3 here, 0.3 here, and we distribute that here to the whatever it was 0.1. I add 0.5 here, 0.5, 0.05, 0.05, 0.05 here. After you normalize that, it becomes 0.17, and that was not easy to understand there. So after you normalize means if you add this one, it comes out to be only 0.92, but you need to make it as a probability distribution. So you divide everything by 0.92, then you get this. That's what normalized values are. That is normalizing by the total value here. So that now it becomes 1.
Okay.
Okay. So the epsilon 1 is this. Alpha 1 is half times 1 minus. You can see the formula here. I don't know. Can you see this one? Half times logarithm of 1 minus epsilon divided by epsilon. That's what this one is. Alpha is. Gamma is, what is gamma? 0.5 minus F16. 0.5 minus F16. What is F16? F16 is this one. Okay. F16, right? Yeah, F16. That is 0.5 F16 gamma. I mean, this gamma squares are, it's not there. Okay. Don't worry about it. No, this is at what speed it is going to converge. So don't worry about it. So you know alpha 1 how to calculate, what to calculate Z1, how to calculate the normal, what is meant by normalization here, normalizing here, and how do we boost these values here. 0.3, alpha, that's good enough to boost all these things for you. But then if you boost it, you don't get 100% here, so you normalize it to get 100%, and whatever you get is the final weight. Are you with me?
Yes.
Excellent.
Yes, sir.
Super. Now in the second, you remember 3 points were misclassified. That is, if you keep going all the way here, the negative ones are misclassified. These are all negative ones, right? These are misclassified in the second step. You remember that?
Yes.
Now,
Yes, sir.
I have only these probabilities. This is the assigned probabilities. Now I have to boost them. And that is what is happening here. Boosted, it becomes 0.14, but then I have to normalize it because if I add all these things, it is becoming only 0.82. I divide all these things by 0.82 so that you get 1. And after that, it becomes like this, 0.17, 0.17, 0.17. Rest of them are all 0.05, 0.11, and like that. In the third, I do the same thing and it's done. Okay, conversion is done. That's what this one is. The third one. Okay, sorry. The third one. Now it is small. I don't know what. Okay, I don't know what it's to. Maybe it is better this way. Okay. By this the third one, it's the problem is solved. Okay. So my point is you see how to do the boosting and how it's all done by computer. You don't have to worry about it. Are you with me?
Yes, sir.
So you don't have to worry about
Yes, sir.
It's all done by computer. So I just want to tell you to believe, you can now feel more confident. Oh my goodness, this is what is happening in boosting. Yeah, I believe in that. Now I can work on it. I can agree to it and so on, right? So
Yes, sir.
I added the 2 more points and then asked you to fill up as an exercise. That's what this exercise is about. Okay. You just have to follow exactly what I said. Are you with me? So it's an exercise that I have here for 12 points instead of 10 points. 12, so that's a AdaBoost calculation worksheet. It's a sheet you have the data like this, you just have to finish it, complete it. Okay. So that is about AdaBoost, and I want to introduce next time what is called the XGBoost. Okay, XGBoost is a killer. You can't beat XGBoost. That's the end of the story. Why? Because XGBoost adjusts for the parameters, so it avoids overfitting. And how they strategize to take care of the overfitting, next class, tomorrow morning.
Okay.
My time tomorrow morning, your time tomorrow evening, India. Okay?
Yes, sir.
How do you feel, Nini?
Good, sir.
So tomorrow we'll see how to make sure that, because the boosting, I can build lots and lots of trees, even in boosting, right? But unless I penalize, it's not a good model. And this guy did it. One graduate student did it, and he is the one who helped build this robot, data robot. And they are going to go to public, and that guy will get probably tons of millions of dollars. Who knows, $100 million? Okay, because he's such an important person in the organization. He did this job, XGBoost. 2 kids actually, 2 Chinese kids. I don't know whether it's a good idea to say Chinese, Indians, Americans, and all, but they're little kids, so I just take the privilege to say that, because it's a phenomenal invention they did, but it's a very simple idea. So what is that simple idea? Why other people missed it? We will see tomorrow.
Okay.
Thank you very much, everybody. Have a nice good night.
Thank you, sir.
Great day.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome. See you tomorrow.
Good night, sir.
Yeah, tomorrow morning,
Bye, Nini.
our time,
Question.
US time, your time is 7
Evening.
9 a.m. I still keep the 9 a.m. or 8 a.m. 9 a.m.
For you is 9.
You have to keep it 9. Yes. Okay. 9 US time, which means your time is 8:30.
8. Yes.
8:30.
Yeah.
Check it out. You got to check it out. If Central time is 9 a.m., what is my time? Check it out. Okay. Now I have a call to make to somebody in India. Okay, because of
We had a time change.
yeah, because of time change. Okay. Thanks a lot, everybody. Have a good night, Nini, and good day.
Thank you, sir.
You too, sir.
Good
Thank
night,
you.
sir.
Bye.
Yes, sir.
Bye.
Bye, Nini.
Yeah,
Bye, sir.
Bye.
Bye. I have a quick
Bye.
question for you. Can I call you?
Who?
Well, I have a quick question for you. Can I speak with you? Just 5 minutes. Maybe another time I'll talk to you. Don't worry about it. If you are busy, okay. Getting late also, okay. We'll talk another time. Thank you.
Okay. Thank you.
Bye. Bye.
Bye.